Hello everyone, I'm Dr. Moira Gutu. I'm teaching Advanced Machine Technology and Engineering course, advanced course which is delivered for manufacturing students in master's program. So this is chapter 2 where cutting mechanics of hard materials. So when we see the objective of this course is to introduce a student the science of machining hard materials. So how to machine hard materials, what materials be fell under hard uh, categories. So the students will know how to machine hard materials with conventional machining and non-conventional machining also. So in this, we will see the feature of hard material cutting. What are the features or the properties of hard materials? The designation brittle, often used in manufacturing characteristics, a certain material group according to their mechanical property. So to say it is a brittle or a ductile material, it is based on the mechanical property of the material. So the hardness represents a combination of material properties that determines their machinability and workability properties. So they have high brittleness, low fracture resistance, means the hard materials can easily fracture. So machining the hard materials imposes a challenge on the cutting tool and as well as to get high surface finish during machining. So the cutting of hardened ferrous materials and hard coatings with hardness above 47 Rockwell hardness number is called hard materials. So any materials which can fail under the Rockwell hardness number are on 47 and above is categorized as hard material machining. So these hard materials have been machined by conventional method like grinding, or it can be by milling, also it can be by turning, by diamond turning process. Otherwise, we can machine also these hard materials using non-conventional machining techniques, which we will see later on chapter 5. The hard materials, they have some properties like the brittle materials are high performance ceramics are brittle materials, glasses, glass ceramics, quartz, safari, and calcium fluoride also, silicon, germanium, and ceramic matrix composites are fell under brittle materials. This means they are hard materials which are difficult for machining. They have these characteristics mainly. They have low fracture toughness, means they can not assess toughness or they cannot absorb load when the load is vertically or horizontally applied upon the hard materials. They can easily fracture. So they do have low fracture toughness. They have low fracture strain also. Uh, they cannot easily strain or deform. Temperature resistance, this got them high application areas in semiconductor industries because they can resist high temperature up to 3000 degrees Celsius. They have chemical resistance so that they can be used in chemical industries, acid industries. They can use these hard materials because they do have high chemical resistance, like ceramics, high hardness. The hardness is also very high. And you see the application areas of this hard material, they have numerous applications where high technologies are applicable, like semiconductor industries, optics, they can use ceramics here, and they can use the automotive industries and medical engineering. They have a lot of applications, not only restricted to this one. Well, if you see the machining behavior of brittle materials, what the brittle materials will have during machining, we will see in this category. So the machinability of brittle materials significantly variable in contrast to metallic materials. This means the hard materials, ceramic like glasses, they are significantly different from metallic materials. When machining brittle materials as opposed to machining ductile materials with increasing penetration depth, the material separation becomes dominated by the characteristic behavior of the brittle material. So there is a formation of microcracks and the resultant fragment breakaways of the materials. So this has its own problem because the cutting tool can crack also. The machine surface is difficult to get a required smooth surface finish. So these are the behavior of these hard materials. So we have to approach machining the hard materials in such a way that the science and the features to apply the cutting tools should be based on research. So as the grain cutting edge penetrates into the brittle materials, radial and the lateral crack form in the tool material. So when the tool material has a high cutting load applied on it, a high cutting load is applied on the workpiece material, there may be a formation of a lateral cracks in a tool. Okay, so if this is a tool and the tool may have a crack will start in the tool material because of the hardness of the workpiece material. The actual chip removal in this case takes place by means of lateral cracks. So the chip removal is in the direction of lateral cracks, which cause spalling of the material. Whereas the axial cracks lead, on the other hand, to penetrate the damage to the tool external layer. So what is good is here, the material removal is in lateral cracks formations, and the axial cracks can damage a cutting tool. So such subsurface damage, non-detectable with commonly used quality testing methods, can lead to premature failure. So this means if the axial crack can develop in the cutting tool, and it is a subsurface defect, so it can be observed the defect below the surface. So this is a very difficult thing. You cannot detect or non-detectable with commonly used quality testing methods. So it can cause what early failure of a cutting tool, early failure of a cutting tool. So by any means in machining hard materials, you have to remove the axial crack, which can be formed in the workpiece material as well as in the cutting tool materials. So I will see here the difference between machining brittle materials and ductile materials. So when here the load, the cutting load is applied here, this is a cutting tool and this is a workpiece material. So this is uncut chip thickness or the depth of cut. So when the load is applied and this is cutting velocity, the cutting velocity or machining speed, this is the tangential load and this is the axial load. So the machining will carry form in this direction, whereas the crack may form it as the axial crack inside the workpiece material, which is not good. This is a lateral crack in this direction. It is this one is more important, means it is good, it is machining direction. So you see uncut chip thickness or the depth of cuts matters how we can avoid the axial crack, which should be avoided in machining hard materials. Okay, is it clear? Okay. In the ductile materials, the depth of cut is very small, and here, as you see, there is no lateral crack as the machining brittle materials because it is easily plastic deformation, whereas it is cracks can form it the chip grooves here, it is very smooth, okay, machine surface. So this is the optical microscopy image of the machine surface. When you see the difference between this and this one for brittle materials, there is a lot of fragments due to the imposed cutting load and the material behavior, which is not smooth. But one objective of machining is to get smooth surface. But if you see ductile materials, here you will see the grain structure is very smooth. The machined surface is very smooth also. So this indicates us that machining hard material is a bit difficult, and you have to approach by research and scientific method. Will a ductile chip removal also be released in the case of brittle materials? This means even if you are machining a brittle materials, a ductile chip removal can be maintained, or you can achieve a ductile chip removal process. To achieve this, the reduced chip thickness are necessary. There is a formula which is reduced chip thickness, so not exceeding a critical value. HCU, reduced chip thickness value, is equals to 0.15 times E, it is the Young's modulus of a material, over the hardness of the material, times this one, the fracture toughness of the material, Kc, over the hardness of the material, the whole square. This shows that the machining of hard materials mainly depends on the hardness of the material. So if the H value, the hardness is very high, the hardness is high for the material, the HC, reduced chip thickness value, should be very small, okay, very small. So from here to determine the machinability of hard materials, it depends on three factors: the hardness of the material, the Young's modulus, and the fracture toughness of the material. So the material which has low hardness can be easily machined, to say. Well, the machining high performance ceramics. Now we will see what materials are there in the machining of hard materials. We have said glasses, ceramics, and a lot of oxides. So we will see one by one. With respect to their material characterization, ceramics are subdivided into three. Oxide ceramics are there, non-oxide ceramics, and silicate ceramics. In the case of oxide ceramics, aluminum oxide and zirconium oxide represent the industrial most important materials. Means they have a huge industrial applications, zirconium oxide and aluminum oxide. Oxide ceramics have mostly ionic bonds. More than 60% they are ionic bond, exhibit favorable sintering properties, and are disadvantages compared to other ceramic with respect to their heat resistance. The carbides are like boron carbides, silicon carbides, nitrides, silicon nitrides, and boron nitrides. Silicates are included first and foremost with non-oxidic ceramics. So non-oxide ceramics are like silicon carbides, I said, boron carbides, and silicon nitrides. They have high percentage of covalent bonds, up to 5 to 40%. They are covalent bonds, which in combination with a small interatomic distance leads to high chemical and thermal stability. So one of the advantage of ceramic material is they have interatomic distances are very, very crowded. So that this has the advantage for them to have high thermal stability. This means they can resist high temperature. Because of this, the ceramics can be used in furnace in industry, in melting of this metallic melting furnace, and also industrial application like semiconductors. So they have interatomic distance is very, very small. They bring about high strength and hardness and limited ductility. This claims that hard materials are very brittle and they have limited ductility, which causes them difficult in machining. Silicate ceramics are first separated into coarse ceramics and fine ceramics. The coarse ceramics in silicate include magnesite, mullet, silica, or zirconia stones. They are coarse. The silicate ceramics which fell into fine ceramic category are glass ceramics and statites and corrodites. As opposed to the metal machining, when processing ceramics, the cutting forces are high. Okay, in machining ceramics, the cutting forces are very high due to the hardness of the materials, which is opposite to machining metals, which are ductile, especially in normal direction. Force be absorbed by correspondingly rigid machines. So when machining the hard materials, the cutting forces are very huge, so you need a rigid machines which can avoid what vibration. Otherwise, excessively soft relation systems lead to decreased dimensional and formal accuracy in the functional surface. Sorry. So it can when there is if the machine is not very rigid, if there is a vibration, they can cause what inaccuracy in machining, and you cannot maintain what dimensional accuracy or form accuracy is very low. Diamond grinding wheels are used for grinding ceramic materials. So the conventional grinding wheels cannot be used to machine ceramic materials. They can be used by diamond machine, diamond grinding wheels. Okay, so the diamond grinding wheels are strong thermal loads. They can resist strong thermal loading. Increased diamonds are placed on cooling lubricant supplies. When you use a diamond cutting tool, you have to use also lubricants. Concerning the type of the bond, tools bond with synthetic resins and metallics are the most often used ceramic grinders. They are synthetic resins, and the cutting tools or diamond cutting tools should be coated one. So the grinding wheels bonded with synthetic resin exhibit more wear during the process, but lower process forces. So the cutting force is low when you are using the bonded with synthetic resin grinding tools. But one advantage is the cutting force can be lower, but the tool will wear easily. Therefore, results as a rule in a better surface quality and formal accuracy can be achieved when you are using a diamond cutting grinding tools, which are synthetic resin bonded surfaces. Okay, the size of the diamond grinding used varies between D7 up to D252. This is a standard of a diamond, diamond grinding wheels. So when you purchase the diamond grinding wheels, the standards fares between this range, D7 up to D252, whereby the grain size matters also between D91 up to D181. The grain size are selected for most machining operations. The grain concentration in ceramic machining are usually between C75 and C100. So among the grain concentrations, when machining ceramics, you have to order or use only these ranges. Glass machining, in oxide glasses, both covalent and ionic bonds predominate. So in the glasses, they have both covalent and ionic bonds. It is clear. They generally display strong polarization, which also causes it is characteristically brittle removal behaviors. When machining a glass also, it can easily brittle, and it is cause a difficulty in machining. When material fractured, the bonds when the material fractures the bonds of the glass, the structure of the glass is destroyed irrepeatable. So the structure cannot recover during machining of glasses. So this is a very difficult for machining unless we use a very scientific methods to machine. As opposed to the metals, the free electrons of which can form new bonds. So if you see the machining ceramics, they can be the material removal is in the form of micro grooves. Here, the micro grooves, you will see the groove depth, the groove width is there, and this direction. So this is the machining in this direction. You will see the fracture here. During glass machining, it will fracture, and this fracture can easily propagate into the workpiece material. So the micro fatigue also during machining glasses, the micro fatigue is one formation of material removal process. The fatigue is, as you know, when a repeatable cyclic loads is applied on the workpiece material by a cutting tool, then the material removal or the chip formation is in the form of micro fatigue. The other one is micro crack formation. This is a very bad machining technique of ceramic. You better avoid micro crack formation. Here, the crack is not uniform, and although the material is removing, but the crack formation is a danger process. Micro cutting. This is a little good micro cutting. The form of this one, machining depth. Material removed can be in the form of micro cutting process. The material behavior of glasses when penetrated by an abrasive cutting edge with increasing chip thickness until exceeding the critical chip thickness, which I explained already, depend on the hardness of the material, the Young's modulus, and fracture toughness of the material, which initiates micro cracks. Okay. The ductile machining process is also realizable for these materials despite their amorphous structure. You know that the glasses are amorphous structures. The structures are not uniform or repeatable like a metal. So when you're machining, you will see different grain structures, which causes fragmentation of the chip removal process difficult. The creation of damage-free external component arises is also possible for glasses by means of machining mechanisms. It is assumed that highly negative cutting angles need to be employed for ductile material removal in order to obtain a condition of hydrostatic compressive stresses. So a negative cutting angle for a cutting tool engaged with a workpiece is for machining ductile material imposes on hydrostatic compressive stresses. Beyond that, several further measures are helpful in reducing individual chip thicknesses. So the other one, to reduce the chip thickness, in addition to using negative cutting angles, you can use the use of smaller granulations. Means the use of smaller granulations means the grain structures should be very fine, very small. Higher grain concentration. This avoids what? The amorphous structure of the glass. Low feed rates. You have to reduce the feed rate very low, not as high as ductile material machining. Low depths of cuts, high cutting speeds. It has, of course, a limited value, which is optimized value. You cannot simply say high. How much high is it? It should be specified based on the optimizing the cutting tool parameter. A high radial accuracy of a grinding width. The use of ultra precision machining is also required. We'll see this one in chapter 5. Ultra precision machining is with high surface finish. So the development of cutting materials of high hardness and heat resistance made possible machining of hard turning is possible, hard milling is possible, okay, hard drilling is possible also. as far as you have high cutting materials like ceramic materials, diamond materials, and boron nitride cutting tools, and they have which have high heat resistance capabilities. You can machine what hard turning, hard milling, and hard drilling processes. We will see one by one what is hard turning. So in turning, the cutting edge is usually continuously engaged. So in turning, the cutting edge of the cutting tool is continuously engaged with workpiece material. Okay, the cutting tool is continuously this tool, cutting tool. This one is uncut chip thickness or the depth of cuts. This is cutting chip thickness. You will have angles here, the cutting angles, the relief angle, and the rake angle of the cutting tool. Engaged with the workpiece material. This is a workpiece, machined workpiece. So in turning, the cutting edge is usually continuously engaged. I want to show you that the machining of turning, milling, and drilling are different. So in turning, the cutting tool is continuously engaged. There is the energy density implemented in the chip formation zone is high. So the energy imposed by the cutting tool on the workpiece is high, which leads to high thermal loads on the cutting edge. So the cutting edge can easily wear because of this continuous engagement. Therefore, a cutting speed must be limited with respect to the tool wear during hard tapping. So cutting ceramics like mixed ceramics of alumina and titanium carbide are applied up to 150 meters per minute. The maximum cutting speed reaches up to 150 for machining of oxide ceramics and non-oxide ceramic like titanium carbide. Polycrystalline boron nitrides can be used also up to 220 meters per minute cutting speed. Usual cutting depths are in the ranges of, you see, the cutting depths, or which I say this one, the cutting depths can be up to 0.05 up to 0.3 millimeter, which is very, very small. So there is a limited range or optimized range uh, which can be investigated through a research. We have a maximum limit for using a cutting speed when machining these ceramics or hard turning using mixed ceramic and titanium carbide cutting tools, boron nitride cutting tools. So feeds significantly determines the surface quality. So the feed rates, which is up to 0.05 up to 0.2 millimeter, can be applicable depending on the requirement of the surface roughness. The feeds during machining of hard turning can reach up to maximum 0.2 millimeter. The tool life depends significantly on the hardness of the material, as shown in the tendency illustrations referring to the hardened steel materials. You will see for hard turning, for hard drilling and hard milling, the cutting materials, the cutting parameters are put here. The cutting speed, VC is cutting speed, the feed rate, and the cutting speed for hard drilling carbide, titanium carbide coated material, the roughness or the accuracy level, the RZ, the hardness, which is more important, which indicates the level of smoothness of the machine surface, should reach up to 1 up to 3 micrometers. So it is at micro surface finishing process. Here, hard milling. So in hard milling, if you see here, the cutting speed is up from 200 up to 350. So you may use also here more related to the hard turning process during milling process. When you compare the surface finish is more smooth when you are using hard turning. It can be maximum up to 1 micrometer. Here it is up to 2 micrometer. The, the maximum is good in machining. The maximum is the smallest one here, small surface. The feed rates are also specified for hard drilling, hard milling, and hard turning process. This research is done for steel material. So in hard turning, one usually work with relatively low feed rates and large corner radius. The large corner radius is helpful for energy dissipation. It means the energy concentration at the tip of the cutting tool can easily dissipate, or it can easily transform to the tool material. So the heat concentration at the engaged surface can be less, which can prolong the cutting tool life. This allows the keeping of the cutting edge load with limits. Is the load, the cutting load, the cutting force which imposed on the cutting tool can be limited if we use a low feed rate and large corner radius. Okay, you have to see the signs how the low feed rates and large corner radius will reduce the cutting force and will help to reduce the cutting tool damage. You have to know this one. This is the science-based study here. This graph shows the tool life versus the cutting speed for cubic boron nitride cutting tools. Steel, hardened steel, it is hardened steel. So if you see here, the tool life mainly reduces. The tool life is going reducing as the hardness of the material increases. So you will have more tool life up to 500 maybe or 450 meters minute. Tool life is in minutes, and the tool life is very low. Okay, up to 30 minutes maybe when the hardness, Rockwell hardness number reaches up to 65. So this shows when you machine hard materials, your cutting tool easily deteriorates. Means you are going to replace a cutting tool which is not economical. The manufacturing cost can be high and the machining cost can be high. So here, the second graph, you will see the tool life for different hardness materials. Okay, here the cutting speed. Also, the tool life depends on the cutting speed. As you increase the cutting speed from 80 up to 250 meters per minute for every hardness materials. This material is chromium, molybdenum, vanadium alloy, which has 52 Rockwell hardness number. And this one is chromium and chromium alloy materials, which has the Rockwell hardness number, which is 60 to 62. And this material here, the maximum hardness material, which is 65 Rockwell hardness number. Rockwell hardness number. So when you machining the more hard material, which when you compare it to 52 and 62 and 65 Rockwell hardness number of these chromium materials, the tool life is limited up to this for the hard material. So machining less hard materials from the last equation I've shown you, the tool life is directly related to the hardness of the workpiece material. So the tool life is high when H, the hardness of the work material, is low. The tool life is high. Tool life is increasing. When compared to the cutting speed for every materials, whether it is 52 or 62, And the beginning, the tool life is more when the cutting speed is low. As the cutting speed increases, the tool life deteriorates for every material here. These are the value of feeds. Okay. An advantage of hard turning is flexibility of the process. What does this mean? In hard turning, the process is flexible, means the workpiece is machined by the controlled systems. Whereas when using grinding, it is mostly machined by plunge grinding, or at least by copying the profile of the grinding wheel into the workpiece. So the flexibility is this one. The profile of the grinding or the profile of a cutting tool is imposed on the workpiece material during grinding, but during turning, it is not like that. With any shape of the turning tool, you can machine the surface profile which you can require. This allows its flexibility. In turning, workpiece can be machined by one or several tools which are easily changeable. See? The cutting tools can be easily changeable. You can machine also within a single cutting tool or several cutting tools by changing, or either simultaneously also. It is possible simultaneously machining with a multi-cutting tool. This often leads to a considerable shortening of the process chain in the sense of completing machining. So to less complexity costs and to lower investments. Means it will reduce, it will increase what? Productivity when you use multi-cutting hard turning process. We'll see hard drilling here. Hard drilling, you know that drilling is imposing a hole onto the workpiece, and for that we can use a drill bits. So in hard drilling can be also possible in conventional machining of hard materials which have a hardness number above 47 Rockwell hardness number. So in hard drilling, we'll see the signs. Holes also have to be regularly brought into turned parts. Means the holes should be smooth, regardless of whether the hard workpiece are manufactured by grinding, turning, or milling. Such parts must be machined by hard drilling process. For the case of hardened workpiece, parts with 0.5 up to 1.5 millimeter thick layers and tough base materials can be observed. Additional difficulty often arises that one has to drill in the hard as well as a soft textures. So in drilling hardened coated materials, we will have what? Different hardnesses. In the above one, you will have hard coating materials, a case hardened material, which are tough. And also as you move down, you may have also the soft parts, soft surface parts of the material. So this will have the energy differences in so energy differences in cutting the tool or a drill bit engagement with a hard work with material. So solid carbohydrates are generally applied in fine grain carbides. In drilling hard materials, you can use solid carbohydrates with the fine grain carbides. So the fine grains, the coarse grains, determines the strength of the material, the hardness of the material of the cutting tool. So the drilling tools with the cutting inserts are only used for large diameters. So drilling hard materials with a cutting inserts can be used for drilling large diameters. Otherwise, you can use solid drill bits for machining small holes. For this purpose, the tools coated with titanium nitride have been introduced. They offer the advantage of minimizing the friction between the drill and the bore walls and between the chip and the flute, in addition to wear reduction. So this means the coated titanium nitrides can reduce what? The friction imposed during machining, because the twisting or revolving the drill bits can produce at high temperature, and as well as the high tool wear can be produced. So to reduce high tool wear of the cutting tool, the friction coefficient or the friction force should be reduced. For that, coated titanium nitrides are very useful because coating can reduce friction resistance of a material. Under finishing conditions, the dimensional accuracy in the ranges of IT is the symbol for international tolerance, and the IT is up to 7, IT up to 9. The surface quality RZ, the roughness level is 2 up to 4 micrometer. The smooth surface is 2 micrometer and the rough surface is 4 micrometer. In special cases also, the RZ is 1 micrometer. Means drilling up to 1 micrometer will get you very, very smooth surfaces. Or the smooth surface in machining, in the machining surface, if you get a smooth surface, either in turning, drilling, or milling, you will have wear resistance and corrosion resistance surfaces can develop, because capability of the tool materials will determine the level of the machined surface finish, corrected by hard drilling with solid carbide drills. You see, so drilling a very fine surface finish up to 1 micrometer can be achieved by solid carbide drills. You cannot use the inserts here. Cutting tool inserts can be used only for machining large diameter workpieces. This is in case of drilling. This is the research conducted to test the effect of feet on tool life during drilling, the effect of cutting speed, VC, meter per minute on tool life. As well, also you will see that during drilling, at the feed rate is increasing. As the feed rate is increasing, the tool life is decreasing. The tool life keep on decreasing. So you have to use what? A small feed rates, 0 up to 0.1 millimeter depth in drilling of hard materials. Here, if you compare also with a VC or cutting velocity, 50 meter per minute. See, so if the cutting velocity is from 25 up to 160 meter per minute, the cutting tool life will change also. So as the speed increases, as the cutting velocity increases, the tool life deteriorates. As even though for different materials, you will have optimized cutting speed, optimized cutting feed for a given workpiece material. And you cannot say that the tool life is good here for this material. The tool life is optimum in this case at low cutting speed, 25 millimeter. You cannot say, because it depends on the workpiece material. This may be achieved for a specific workpiece material, but when you change the workpiece material, the optimized cutting parameters should be investigated by research. Tool life for hard drilling depends on the cutting parameters. I told you it depends on feed, cutting speed, and the depth of cut also. So the heat dissipation, okay, one of the greatest problem in drilling is the heat concentration at the drill bit engagement with the hard workpiece is high. So we need a cutting tool which can dissipate the heat along its bodies, so that the heat concentration which can make more deformation of the cutting tool can be easier. So the heat dissipation is particularly unfavorable when hard drilling. So it is difficult for heat dissipation because the drill bits are revolving at high speeds and the heat generation is increasing. So the tip of a drill bit can be easily wear off due to high power density because of the hardness and the strength in generated, and on the hard material, the heat dissipation form the drill point disabled. So the drill point can be more damaged. The cutting tool heats up heavily during the drilling operation, expands and can be heat up additionally by the wall friction, and consequently it clamps, means it can fail. So at that time, the tool life is less, or you are going to replace your drill bit, and the machining economics is very low, means high manufacturing cost can be formed. Therefore, it has been proven to form the drilling tool with a shallow conical tappers. So the shallow conical tapper of a drill bit can form what the circulation of cutting fluids maybe, or the air which can be used as a cutting fluid, so that it can reduce the frictional force, and the tool life is more. Third one, we see hard milling. Also, the milling cutter can be continuously engaged with the workpiece material, and in this case also the heat generation is more next to drilling. And hard milling is applied in mechanical engineering and tool making technology. So milling, as you know, to make a surface finish or flat surface, or using milling you can make holes, also you can make slots. So hard materials can be made or machined by milling. You can say that hard milling, the finishing of sliding gauge-way surface for machine tools requires elaborate guide-ways grinding machines, representing significant investment because of their large work areas. This means it is to show that the machine surface should be very rigid, means very strong milling machines. You need to machine hard milling operation. Compared to turning and drilling, significantly high cutting speeds and feed rates are used. So the feed rates and high cutting speed compared to turning and drilling can be applicable for hard milling. Milling cutting edge is engaged only time-wise, means they can once engage with the cutting tool, and the other one they can be out. So which does result in the thermal and mechanical loading occurring shock-wise. So it is intermittent, not continuous. But the temperature level in cutting wedge is significantly lower. The intermittent engagement of the milling edge with the workpiece can allow what? The lubrications and the air cooling system. So in that case, the levels of the temperature is very low. It can add for tool life. Here you will see the cutting speeds. Here also the flank wear and widths, flank wear and flank widths of the milling cutter with the milling path. The milling path is the length of the depth of during milling operation. So the flank wear increases as you increase VB or milling passes. So the flank wear is more, or when you use less milling passes, the flank wear is here. So the tool life is more at this point than at this point. Here you will see these are the only when this research is conducted, the angles, the relief angles, the rake angles, and the clearance angles range are here. When you do a research, also you have to mention what relief angle, what cutting clearance angle and rake angle you have used. You have to mention. You have to mention also the required surface finish you obtain, the VC, the cutting velocity. For the dimensional and form accuracy needs, one has to consider that by heating the component, by inserting or releasing residual stresses, and due to the temperature variation of the machine, systemic errors can occur. So this means you can heat the workpiece material before hard milling also. This will heating to some level the workpiece material will reduce what it can stabilize residual stresses in the machine surface. So we will see in hybrid machining process, I think in chapter 5, we will see where another technology is applied during machining also. This we'll call the hybrid technology. It will facilitate easily removal of the chips from the hard workpiece material. So heating the workpiece material, heating the component is one technique to reduce the tool wear or to allow easy material removal in hard milling operation. This will help in reducing residual stresses formed during machining. The chip formation. What is the chip formation during hard cutting? In hard cutting, the question raises as to whether the hard materials or the hardened metals can endure such high deformation or whether there is a risk of crack occurring. There is high deformation of the workpiece material. There is a high formation of crack in the workpiece material in the newly generated surface due to insufficient deformability. In machining, I told you we need high deformability, means it should be easily machined. So the cutting tool life can be more and the machine surface can be smooth. Large compressive stresses, it is clear that machining imposes a compressive stress, not a tensile stress, with a high proportion of hydrostatic pressure occurs in the chip formation zone due to the low and deformed chip thickness. And the low and deformed chip thickness, it reminds that it is the depth of cut, and the strong negative rake angle is required. The critical flow shear stress is reached without a material cracking. If you have this, large compressive stresses will be reduced and the deformation is very easy, and the undeformed chip thickness is very small. The depth of cut is very small, and you can use a strong negative rake angle. You can easily machine by hard cutting, hard drilling, or hard turning techniques. As a result of small and deformed chip thickness, the chip formation takes place entirely in the region of the rake face, chamfer, the cutting edge radius respectively. So this leads to the larger already described several negative rake angles. Passive forces. Passive force becomes the dominant force component in hard turning. So furthermore, using tools with a large corner radius leads to a large contact lengths. Last time in previous we have said on a large contact, a large corner radius will allow what the heat dissipation we have said, but it has another negative effect. In this case, the tool engagement with the workpiece is more. So the hydrostatic pressure load on the workpiece is more, which also contribute to high passive forces. Result forces components depend on the tool weight. So the more hydrostatic cutting forces applied may increase the level of crack formation in the workpiece. So this leads to extremely high pressing in the contact area between the workpiece and the flank force of the tool, resulting in high mechanical and thermal loading, which should be avoidable. The hardness of the material has great importance on the force components, we have said already. So this is a research conducted here for different K value materials. K is the fracture toughness of the material. This is the Vickers hardness numbers. See here the cutting force component. The cutting force component is here is very low for the ductile workpieces. We cannot say actually ductile in hard materials. For material which has low hardness, Vickers hardness, VH. So here the fracture toughness of the material is more, okay, is increasing at the hardness of the material reaches up to 1000 Vickers hardness number. So the cutting force components increases with the Vickers hardness number. So these are the result of the experiment. These are the experiment parameters when they are machining the component of rake angles and other important angles. The Z, the surface finish. The Z is feed rate, VC cutting speeds, and obtained surface finish. Sure. So the force effect when turning soft and hard steel materials, you will see here a material. This is a force. It is the force to the length of the workpiece. Fz to AC, the area of machined surface. So this will be varying for steel material, for chromium material, or hard turning process. So you will see the force and to the ratio of machined length to the force applied to the ratio of the area imposed. The condition when looking at the force related to the contact length, the cutting force to the contact length, LC, and the force related to the contact area is FZ, the force applied to the area, means the machine area. The cutting tool materials and wear. While hard cutting, a tool is subjected to high loading causing abrasive and adhesive wear. So we have seen this one during tool wear in chapter 1. So there is abrasive wear, adhesive wear, and corrosive wear also. But mostly in machining hard materials, we will see abrasive and adhesive wear. The abrasive wear is when the hardness of the material, tool material, the workpiece material is almost near or similar, but the wear mechanism is in abrasive form, when the hardness of the tool and the workpiece material is very far apart, where the adhesive tool wear is when the hardness of between the tool and the workpiece material is almost near or similar. For instance, deposited hard carbides as they typically exist in cold working steel lead to increased abrasive wear. Okay, deposited hard carbides can cause abrasive wears. The cutting materials have to have high hot hardness. Means the hot hardness cutting tool property is the tool material capability to maintain its strength and hardness at high temperature due to this kind of loading. So any tool material should have what high hot hardness. High-speed steels and conventional tungsten carbides are therefore not suitable for hard cutting. You have to remind that the high-speed steel and tungsten carbides cannot be suggested for machining hard cutting. However, applicable are fine and superfine tungsten carbides as well as mixed ceramic and polycrystalline boron nitrides can be used as a cutting tool material for hard turning or hard milling or hard drilling operations. Hard turning is largely covered with mixed ceramics, alumina with titanium carbide, okay, mixed, or cubic boron, polycrystalline cubic boron cutting tools. Both materials can be used in continuous cutting. If, however, interrupted cuts make high demands on the fracture toughness of the cutting material, polycrystalline cubic boron cutting tools can be used. For hard drilling, especially titanium nitride coating, ultrafine tungsten carbides are significantly used. For this application, polycrystalline boron tools can be ceramic tools are not available or are too expensive. These are very expensive cutting tools. Hard milling can be carried out with fine tungsten carbides or PCB also. Hard milling can be conducted with this one. The flank wear, we have said the flank wear and the crater wear are the dominant forces of the cutting tool. Cutting tool wear, okay? So the formation of distinctive cratering is permanently determined by abrasion. So the wear in the flank wear can be also in abrasion form, the form of erosion. Okay, when the very small chips are eroding the surface, the flank wear can be forming. The tool life decisive crateration is the wear of the major flank face of the tool. It is the flank wear on the cutting tool. These are the rake angles. These are the process cutting process parameters used. Hard milling component quality. So in hard machining component quality, what are the final goals to in machining of hard materials, either turning, milling, or drilling? We will see under this chapter. So for the application of components, under this subsection, for the application of components under tribological, corrosive, or dynamic operational loads. Means the machined surface is going to applicable in areas to avoid wear, which is tribological applications, to avoid corrosion, either it is a machine tool or any hand tools. They have to avoid also corrosive, dynamic operational loads. Also, they can have a high load resistance. The properties of their surfaces and subsurface zones are of crucial relevancies. These are the areas of workpiece where property alterations will arise due to the impact of manufacturing process. This affects the geometric as well as the physical material conditions. The geometric condition, physical material condition will. The surface topography and roughness are mainly consulted for the descriptions of the geometric surface properties, whereas the physical properties are described based on the future residual stresses, crystalline structures, and the hardness. You have to differentiate this one. The physical properties, which are future residual stress removed from the workpiece material, okay? And the crystalline structures means after a machined surface, what is the grain structure? Is it fine surfaces or coarse grain surfaces? Also, is it hardness? Is it less hard material generated or more hard machined surfaces generated? Will determine. So thus the hard machining alters the component quality. Better remind this one, okay? The component quality during hard machining are either microgeometric, microgeometry, and physical property of surface zones. I'm going to explain these three. The micro at large scale, at millimeter scale, the micro at micro levels, and the physical property of surface zones. So the machining alters the component quality. What we call the component quality, we will see. A microgeometrical deviations, the hard turning on specially designed precision or high precision. This permits dimensional accuracy in the ISO quality ranges, ITS, IT5 up to IT6. Okay, the hard turning are fell into ISO quality standards. So circularities of 0.2 micrometer. This is the microgeometric deviation, which is international ISO standards. And cylindericity below 1 micrometer are achievable. The average depth of roughness reserved for hard turned surface is approximately 0.5 micrometer. I said to you, this is the average. In the earlier my presentation, we have explained the range where this surface finish can fail for turning, drilling, and milling. But the average acceptable ISO standard for surface roughness is 0.5 micrometer in order to say the component quality at micro level is acceptable. So the impact is on the micro, the large geometric deviation, meaning deviations of the form, dimensional, and position. The deviation in the form, in dimension, and position. So component alteration, which are generally undesired, can be ascribed to all the partial systems involved in the process. The following sources for alterations can be assigned to the partial system, to the workpiece, okay? The microgeometric Deviations can be arised from the workpiece, from the tool, machine, and environment. One by one, we will see how these alterations, which are not not required, will be avoided or caused by the workpiece material, the tool material, the machine's condition, and environment material. The workpiece, the deviation of the dimension, the form, or the position of the raw part. Okay, the accuracy level of hard machining depends upon the quality of the raw part of the workpiece material. The variation in material strength also, the strength level of your material, the activation or introduction of residual stresses, the raw material which you bring to hard machining, whether it has more residual stress or less residual stress, will affect what? The dimensional accuracy, the form accuracy of the machine surface. Locally and temporally variable temperature fields, where you are machining hard material, the temperature situation. Tool, the compliance of the tool and tool holder. What type of the cutting tool you are using, what type of a tool holder you can use. It can determine what the geometrical errors or the form errors on the machine surface. The tool wear, is the tool wear easily have the flank wear or crater wear, or the tool wear is more or less. It can affect the deviations of position during tool changes. Okay, the deviation of position during tool changes. Also, when you are going to change a cutting tool with a new cutting tool after a tool is damaged, the position, the accuracy level of changing your cutting tool determines also the form errors or dimensional errors. Machine. When you see the machine, the geometrical deviations of the machine, is it rigid machine or what type of machine it is? Kinematic deviations, the kinematic deviations which arises from when you are giving feed to the cutting tool, when controlling system to the feed compliances of the machine in force flux, thermally caused deformations. And the machine is not resist thermal loading, the load alteration during machining also. Environmental, the environment, external heat sources like radiation or is it cryogenic application. It can affect the final surface finish of your hard material machining. Alteration of environmental temperature, convection also. And the convection, radiation, this is the mode of heat transfer from the cutting tool to the workpiece or from the workpiece to a cutting tool. Alterations of the cutting fluid also, where you are using a cutting fluid, it can affect the final form deviations of the machine surface. For example, the increase in cutting force resulting from deviations in the material strength has an increased impact the higher the compliance of the machine. The forces active in the process as well as the connected heating of tool and the workpiece influence the accuracy of the form and deviations. Tool wheel alters the position of the cutting edge and can thus directly result in deviation of dimension and forms. These are the micro things. When you see a micro geometric properties, a very at micro level geometric property of machined hard material. The surface roughness after hard turning is fundamentally influenced by choice of cutting angle radius, the cutting speed and fit. It's initially surprising that roughness increases with a lower speed. At the lower speed, the roughness is more, means at the engagement time. At the engagement time, in order to overcome the huge hydrostatic machining cutting force, the roughness may be high. Once you start increasing cutting speed, we are going to get high surface finish. Even though there is a maximum level, optimized level of cutting speed should be there. Since the dynamic effect decreases due to imbalance incitements. So The explanation is that lower speeds increasingly lead to irregular segmented chip formation and thus higher surface roughness values. Lower speed is not recommended for high machining. Very high is not recommended also. The recommended cutting speed during hard turning, milling, and drilling should be optimized parameter, which gives a good surface finish. So the surface performance and as a function of cutting speed and fit, I have already explained this one, the roughness level, cutting speed. So the roughness is very high at low cutting speed, and the roughness is, you see, I told you this one is optimized one, 150 meter per minute. At this cutting speed, the roughness is very low. And as you keep on increasing, again, it is going to raise or increase the surface roughness. So this value is optimized value. And it depends also for different material properties. Here also you will see the fit and the roughness of the material increases. The material loses its smoothness as you increase fit. But in the beginning also, at the low fit, the surface roughness is high also. So there is optimized value is this one. For every material, there is an optimized parameter. By research, you have to find that optimized parameter, which is economical for machining. Surface roughness are set with respect to feed for different materials here, different materials. So for all materials, it is going to raise or increase as the feed rate in millimeter is increasing, surface roughness or the surface is losing its smoothness. Physical influence. Along with the geometrical shape of the mechanical surface, the physical property of subsurface zones is very important. We have a top machined surface, we are talking a smooth surface up to 0, up to 1 micrometer, something we have said. But the subsurface microstructure of a machined surface will be very important also for functionability, durability of any machined component. So we matters about maintaining or being effective subsurface microstructure of hard materials. We will see how to examine or characterize, measure the subsurface damage of machine surface. So metallographic and X-ray examinations. Metallographic is a science of investigating or metallography is the science of measuring the microstructure of a surface. The metallography has etching process, characterization process, and measuring the grain size, average grain size. What is a grain structure? Is it dendritic or fine grain, coarse grain? We have to examine by X-ray microstructure, X-ray examination or characterization, or electrodispersive spectroscopy or scanning electron microscopies can be used for characterization. Proves that the hard turning can procreates a considerable influence of subsurface zones. This manifests in altered residual stress conditions. So when the machining is not smooth, when the machining, the tool engagement, either turning or drilling is not smooth, it will cause not only high surface finish, it will cause also subsurface damage, like imposing residual stresses. This residual stress is machining is mostly reduced by heat treatment after machining process. Means stress concentration due to thermal loading or mechanical loading at certain point. This cause irregular surface property or subsurface property. The machined surface can have different strengths, hardness, wear resistance, corrosion resistance, due to the presence of residual stress in the surface or subsurface. So this can be reduced by either right implementation, optimized cutting parameters used in machining hard materials, or a heat treatment process after machining. The development of re-hardened zones as well as in areas of tempered structures. The reason for this behavior are the high stresses and temperature raised during machining of hard materials because of the hardness of the work material is very hard. The structural alteration, other thermal influences can be low. The tool wear on the flank face decisively influences the property of the subsurface zones. So the thermal meshing loads of the subsurface zone raises with an increased tool wear. A cohesive hardened layer which appears white in the polished section and a tempered zone located below which appears dark in the grinding pattern. This will you will understand only after you examine by X-ray microscopy or electron scanning microscopy the machined surface. You will see what the grain structures look like, what the subsurface structures looks like, whether the residual thermal stress can be present or not. You can measure by X-ray diffraction spectroscopy also. So this is one research which shows the level of residual stress in megapascal in machined surface and the depths for different VBC materials. VBC is 50 micrometers. So you will see the workpiece material is magnesium chromium material, which is the hardness, Rockwell hardness is 62. The VC cutting speed is 220. I've seen the feed is 0.1, which is very, very small, and AP is 0.2 millimeter to geometry. These are the required or the cutting tool. So there are two materials, cutting tools, polycrystalline boron tools, boron nitride tools, alumina with combined with titanium carbide, and ceramic matrix materials. For all materials, the level of residual stress is decreasing as the depth increases. But after reaching some optimized parameter, it is again raising or increasing. So we have to reduce formation of residual stress by different techniques, by the preheating the workpiece material, optimized using optimized cutting parameters. The third solution to reduce residual stress formation in machine surfaces heat treatment. Application of hybrid process for hard machining. This is the final subtopic in chapter 2. What is hybrid process in machining? The hybrid process is that can help what? Which can help or which can facilitate machining process during machining. In other way, it can facilitate the formation of smooth surface finish. It can facilitate reducing tool wear. It can facilitate what? The chip formation in machining process. So the hybrid process for hard machining is using two or more than two machining systems together so that it can involve hybrid machining or hybrid manufacturing process, solves problems in hard machining and improve productivity. Productivity means in machining getting high surface finish. Productivity means reducing machining cost, reducing tool wear, and so on. So productivity is not easily maintaining what? High material removal rate, but in cost of reduced what? Tool wear, like in cutting, grinding, forming, and chemical physical process like electric discharge machining, electrochemical machining, and laser beam machining can be engaged to facilitate what? Hard turning, hard milling, and hard drilling process. We will see this one: electro discharge machining, electrochemical machining, and laser beam machining combination with hard turning, hard milling, and hard drilling. Advanced mechanical products such as gas turbines, aerospace applications, automotive parts, and heavy off-road equipment means shipping equipment can be machined with these hybrid technologies. Rely more on advanced material to achieve required performance characteristics. The formation of new materials in order to challenge the environmental failure criteria will cause difficulties in machining industries. So the development of new machining techniques or updating the machining techniques, investigation of new cutting tools which challenges the formation or development of new workpiece material is one challenge in the machining industries. So the classification of hybrid process, the classification or grouping of hybrid process and some examples. The first group, you will see the first group, no, the first group, combination of different energy sources. The second group, controlled application of process mechanisms conventionally done in separated process. So here we see assisted process, laser assisted turning, applying light amplified stimulated emission of radiation. So laser is the one which uses radiation technology in cutting process. So laser application can either the material removal during hard turning process. So we are using laser beam in addition to turning process. So this is hybrid first category. The other one is vibration assisted grinding. We can use vibration technologies in addition to grinding of the workpiece materials. Laser assisted forming or bending process, also the first category of assisted process in hybrid technologies. The second one is mixed processes. The mixed processes are, you can use two processes, machining process together, electric discharge machining and electrochemical machining together, electric discharge machining with grinding process together. So this hybrid technology, as I told you, has to improve productivity, to either the material deformation during hard machining, and to prolong the cutting tool life, and to have reduced machining costs. The second one, a controlled application, is the controlled application is you will have environments of machining should be what controlled by some parameters. Grinding, hardening, form hardening are the second hybrid technologies. The other one is, you will see the other one, for example, here for tool life traveling paths, you will see here, and the flank wear. So for conventional machining, for CO2, means carbon dioxide, laser machining, and LN is nitriding process. So the two life travel paths with increasing the flank wear in micrometer. This is the morphology after characterization of the tool. After machining, they have seen how the wear, the conventional cutting, the cutting length up to this one, the wear, the flank wear depth, the flank wear width can be up to 4 micrometers. You will see here also the wear depth up to 4 micrometers. The flank face nose radius wear off. Here the material removal, you see how the micro cracks is developed in subsurface zone. This is actually the cryogenic cooling milling setup of titanium, vanadium, titanium alloy. This one is a titanium alloy, which is high industrial application, and tool wear behavior in vibration assisted turning, right? So if you have drilling here, you have, and you have the cooling application, but you can assist the drilling process by vibrating more the workpiece in addition to the drilling bit is rotating. Advantage of hybrid technology in machining, they can reduce of process forces. The cutting force can be reduced, I told you, if you use hybrid technology, but they are more economical or more costly. The economical cost is high. Higher material removal rate, productivity can be improved if you use hybrid technology. Reduce the tool will reduce, you will have prolonged tool life, excellent surface quality, smooth surface quality up to micro level you can get, but it is difficult to get at nano level, and high precision, high surface finish. Thank you very much for being attending this advanced machining and engineering technology, which is delivered to Manufacturing Engineering Master's Program courses. Welcome again. We'll continue third chapter, which is machining of composite materials. This course is delivered from the Department of Mechanical Design and Manufacturing Engineering, Adama Science and Technology University. I'm Dr. Moira Guto. Welcome. Goodbye.